Welcome to Grade 12 University Math. This is our diagnostic preparation or our review of Grade 11 University level math to get us started on what we need for this course. So in 3 days, you're going to be given a test which will help us, and that means you and I, your parents, and your guidance counselor determine this is the right course for you. Because you might have picked this course, you probably picked this course last February, right? And it was a long time ago. And maybe you don't need it anymore because of university, you've got a different pathway. Or maybe you need to have a certain mark in this course. So we've got to make sure that you are on track for doing that. So let's review some grade 11 material. And here's what you can do. You need to get out your old grade 11 notes. If you threw them out, that is a shame. You should not have, because that was called grade 11 functions. This is advanced functions. We need all that knowledge. Do all the questions that I assign. So if I assign specific questions, please do them. However, this year, almost all of the time it's going to happen is I'm going to let you choose your own homework questions. I'm not going to pick them for you anymore. You'll need to pick the ones that you need to work on, so you're getting some more freedom, more preparation for actually going away to post-secondary, where your professors will just lecture and walk away, and you have to figure out what you need to do to learn that material. You can form study groups with your peers, really important. Students often do that using different social media. They'll have study groups with each other to help each other and with their homework and everything. Ask questions, really important that you ask me when you're stuck. I will always answer your questions, so please ask them. And lots of practice. So as we say in math, it's not practice makes perfect, but it is perfect practice makes perfect. So you have to do your homework right. If you do it wrong all the time and you do 10 questions all wrong, then you've ingrained it into your brain to do it that way, and on the test you'll still do it wrong. So check every question, check the answer all the time. Make sure you're getting them right. So you should have printed out or have downloaded and you're following along with the handout that matches this PowerPoint. We're going to look at example 1 here. Given the quadratic function f at x, so it's quadratic because it has a power of 2 in it, find f at -2. So review from grade 11, f at -2, that means everywhere I had an x, I have to replace it with a -2. So I have this, it's called a Wacom tablet here, it's pen tab. Sometimes it skips, so if it skips, I'll just try to write over it, but you might notice it and I haven't noticed it. So if you hear me say something and I don't write it down, it could just be the pen. So the first thing I'm going to do is everywhere that there was an x, I'm going to put a -2 there, but you have to substitute using brackets. Proper form is really important, and you're going to lose marks this year very often if you don't follow the right form in math. It's like in English class not putting a period at the end of a sentence or not capitalizing, right? You lose marks for that. So I substituted in a -2 every place there was an x. Now I'm going to follow the order of operations and I'm going to simplify this, but I'm going to press pause and give you a second to work it out. You should press pause too. When I restart this, I will have the whole answer written down. So if you're not there yet, just press pause and figure it out, and let's see if we match up with the right answers in a second. So we're back. The answer is -15. So what we've got is f at -2 equals -15. Another way to write that is this is a coordinate. It is -2, -15. So that's a coordinate we've just found on the quadratic functions, on this quadratic function. Instead of using a table of values, it's just substituting. Let's try example 2. Given the linear function g at x, we want to find g inverse. See that little minus symbol up here? That means inverse. We're looking for the inverse. We did this in grade 11 as well. We're looking for the inverse. So there's a couple of ways to do this, and depending who taught you last year, it might be a different way. The first thing I'm going to do is change this g at x to a y. Y equals -3x plus 7. Okay, it's a little easier in this notation. Now for the inverse, the first step in an inverse is switching x and y. You can also switch at the very end, and your teacher may have done that last year, but I find it a little easier to switch at the beginning. So I'm going to switch, I'm going to put the x, switch the x here, and put the y here. Now, so your first step is to switch X and Y. Your second step is to isolate Y. So I'm going to isolate Y. I'm going to bring this positive 7 over by subtracting 7 from both sides. These are unlike terms, so that's just X minus 7. And now I need to divide by -3. So on my right side here, these are gone. All I'm left with is a Y. But now that Y is isolated, I'm going to put a Y inverse there because I've actually found the inverse of Y. Over on the left side, you cannot have a negative in the denominator. So either you move it out to the front, or you bring it right into the numerator by distributing it. So think of there being brackets here. You can leave the negative out to the front, or you can distribute it in and put -x plus 7 over 3 equals Y inverse. So the other thing you have to ask yourself now is my answer a function? Because if it is, then I should be using function notation. I shouldn't be using this Y anymore. This is a function. Another way to write this is -x over 3 plus 7 over 3. These are all ways of writing the same thing. These are all the same. This last term makes it look a little bit more like a line, right? So I can see, or I could even write it as -1/3 x plus 7/3 equals Y inverse. So my slope would be -1/3. My slope, my y-intercept is 7/3. So this is definitely a function. Lines are all functions. So the inverse of a line is a line, if you don't remember that. If you start off with a linear function, if you start off with a line, its inverse will also be a line. So proper notation here would be, therefore, G inverse at x, because it is a function, is, and you can use any of those three ones there. I'll put the last one, -1/3 x plus 7/3. That's the proper notation because it is a function. But yes, you could have also written it as -x plus 7 if you want over 3, whichever one of those you like better. Okay, so some important points you should have on your page there are the steps for finding an inverse equation, and also is your final answer down here, is this, are you going to use function notation or not? If it's a function, then you have to use function notation. If it's not a function, then you can leave it like that.
For example 3, any function f at x can have some or all of the following transformations. So let's take a look at this. I just put in a sine wave here because a sine wave is one that shows clearly all the different transformations. So the first one says vertical stretch or compression in your bullet list there. So there's a vertical stretch, and now it's going to compress. There it's compressing. All right, so that's a vertical stretch or compression. So that is the a value on your function. So you can draw an arrow down to the a value on your handout or write something in there. So the vertical stretch or compression, the a value is what is changing that. That's what I have typed in the equation here. So let me turn that back to 1. The next bullet is vertical reflection. So vertical reflection, I'll show you what that looks like. Oops. Get that back to 1. Vertical reflection. Here's a vertical reflection. There it's flipped over. It's just moving slowly, but it's just going from an a value of 1 to an a value of -1. That's what I've set the parameters for here. So it's just going, it's doing kind of a vertical compression and reflection there at once. So the vertical reflection is also caused by the a value. The next bullet says vertical translation or shift. So here's a vertical translation or shift. There it is. It's gone off your screen a bit there, but there's your vertical translation or shift. And out of the parameters A, K, D, and C, the one that's responsible for lifting this graph up and down is the C value. The next one we're going to talk about is the horizontal stretch or compression. Horizontal stretch or compression. Here we go. There's a compression, right? So that's all horizontal compression. And once it gets a little further out, it's going to be horizontal stretch. There's a horizontal stretch. So a horizontal stretch or compression, and also it flips over. It's hard to see, but it does flip over. It's a horizontal reflection right there. There's a horizontal reflection. That is the K value. K value does the horizontal stretch, reflection, or compression. And then the last one we're going to talk about is the horizontal shift. So when you're looking at your A, K, D, or C, there's only one of them that it can be. That's only one left over. That's the horizontal translation that you're looking at right there, or shift, and that's the D value. So it doesn't matter what function you're given that you learned from grade 11, the A, K, D, and C all do the same thing, whether I have a sinusoidal like you see right here, or I have a exponential or linear. Any of the graphs you have, they will all do the same thing. So those are, that's your answer for example 3.
Let's look at some definitions here. The first one from grade 11 is the domain. The domain is the set of all x values. It's the horizontal spread. The range is the y values. So think of the max or the min, like of the sinusoidal you just looked at. The highest value and the lowest value are the range. There's a little picture to show you. So the range goes from the top to the bottom. The domain goes from left to right. Domain are your x values and range are your y values, or your f at x values. And then the asymptote is a newer word from last year. It's a line that a graph of a relation or function gets closer and closer to, but never meets some part of the domain. At one place or another, it would never meet it. Example 4. Using set notation, state the domain and range of f at x equals y over x. First of all, this word set notation, this is all we had in grade 11. I never called it set notation because it's the only notation you ever used for domain and range. It's those curly brackets. We're going to learn a new notation this year, so that's why we have to now distinguish between set notation and our new notation. So first of all, state the domain and range of the function 5 over x. All right, so 5 over x, I have a little quick graph here. We're going to do a sketch of it. The parent function, so this is the parent function is, this is reciprocal. Reciprocal, I'm running out of room here. Reciprocal is 1 over x. That's the parent function, right? So the parent function, if you remember, I'm going to do it really quickly. Remember, we can't have a denominator of 0. X cannot equal 0. So we have an asymptote right here. I'm not using a ruler because I can't with my pen tool. We also have another asymptote that runs right along the x-axis here. So the reciprocal function, an easy coordinate for the reciprocal function, if you sub in a 1 for x, you get a 1 for y. So 1, 1 is there. And then if you sub in a 2, you get 1 over 2. So this is 1, 2. You sub in 2, you get a half. You sub in 3, you get a third, and so on. You sub in 1/2, you'll get a 2. So the reciprocal function looks like this. And it's the same in its diagonally opposite quadrant here. There's the reciprocal function. So that's the parent reciprocal function. Now the one we have to do, the only difference is it has an a value of 5. That's the a value there, up on the top. So an a value of 5 means a vertical stretch or reflection. So if you imagine taking this blue one here that I graphed and giving it a vertical stretch, pulling it. So imagine that the ends of it here and here are kind of being pulled and it's being stretched. So it's going to be kind of skinnier, right? And down here and here we're going to get a vertical stretch. So let's see if that's going to affect the domain and the range. The domain and the range of the original reciprocal function are x can't be 0 and y can't be 0. Let me write that down. The original one So the domain of the parent function is x is an element of real numbers such that x cannot equal 0. If you look at the equation I wrote over here, I can sub in anything I want for x. Positive, negative, a fraction, a decimal, a big number, small number, whatever I want, and I'll get an answer, except for 0. So x can't be 0, but it can be anything else. X can be whatever number you want to sub in, go for it. Sub it in, you'll get an answer. So there's our domain. Our range, so if let me just slow this down a bit. The curly brackets here that I'm drawing are for set notation. We start set notation when we're doing range, we're talking about the y's. This Greek letter here, this is an element of. And then real numbers, you can use just a capital R, but usually for number systems, we do an extra bar in there. So this is real numbers, and a straight line means such that, or sometimes you can think of it as except or especially or something like that. With these restrictions, something like that is what that line means. So looking back over at our graph, y can be anything, right? It's going to go, this graph is going to keep going up and up and up and up and up. It's going to never stop. It's going to go up. It's going to go down and down and down and down and down. The only y value, so remember the range is up and down. The only y value it's not going to hit is right here on the x-axis. So the restriction is the same. Y cannot equal 0. And then a curly bracket at the end. So for the function that we're talking about, this f of x, it has an a value, it has a stretch. So this stretch is not changing these restrictions we already had. So even though there would be a vertical stretch here, so for example, if my equation is y equals 5 over x, sorry, and this time I sub in a 1, I'm going to get the coordinate 1, 5 here. So instead of 1, 1, which was this one, I'm going to be 1, 5. So everything's going to be stretched, but we still have the restriction on our denominator. X still can't be 0, and this asymptote here is not going to change either, so we're still going to have y equals 0. So we have the same domain and range that we had before. The a value isn't going to, it's not shifting it up. If we had a c value would lift it all up. That would change the horizontal asymptote. If we had a d value, it would move it from side to side. That would change the vertical asymptote, but the a value or k value, they're not changing those asymptotes. So the domain and range are the same as the parent function. And that notation that you learned last year is called set notation. Next slide. Function, this was your definition from last year. A function is a relation which for every x value there is one and only one y value, just one. So we can easily check it with a vertical line test. So we're going to fill in this chart. I have half the chart on this slide and half the chart on another slide. The first equation we have is of a circle, and the type of relation, I already typed it in there, it's called a circle, but we are also going to put in the parent function equation. So this was a grade 10 one. The parent function equation is x squared plus y squared equals r squared, but the radius that's the parent function is 1. We would just, for r squared, we put in a 1 there. That's the parent function. Now again, with my tablet thing here, I can't use a ruler because it confuses the pen as to what's the pen and what's the ruler. So I have to do this by hand. I would recommend, if I was doing this on the whiteboard at school, I'd be using a meter stick here. So here's my x and y axis. X, y. The circle has a radius of 1, so I'm going to just put a 1 here. That's about 1 unit all the way around here. So my picture would look like this. If I was able to draw a nice circle, it would look like that. That's the parent function. So is that a function, yes or no? So the way we figure that out is if there's any place along that yellow circle that I can draw a vertical line and it hits twice. So I could draw a vertical line right here. There's a vertical line. It doesn't cross my circle at all. That doesn't count. If there's any place at all I could draw a vertical line like here that crosses my function more than once, then it's not a function. So this one crosses twice here. So if you can find any spot at all on your graph where it's going to cross more than once, then it's not a function. Not a function. That was a grade 10 one. Another grade 10 one is the quadratic or the parabola. So the parabola, so the parent equation of a parabola is just y equals x squared. Okay. If I had to graph this one, I would have to complete the square to find the vertex. I know because of the negative a value that it opens down, all that, but I'm only going to graph, the question just says to graph the parent. So the parent graph, y equals x squared, here's my y-axis, here's my x-axis. My parent graph is just the basic parabola. It passes through 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, and the same over here. So there's my parent. I should probably be writing the equation there too. That's y equals x squared. And is that a function? So if I draw a vertical, is there any place there where I could draw a vertical line where it will cross more than once? So if I drew a vertical line here, whoops, it's not very straight. If I drew a vertical line here, it would cross once. Would it cross up here again somewhere? If I kept drawing, no, it wouldn't. So this is a function. Really anything we did in grade 11 is a function. So is this a function, yes or no? Yes, it is a function. Next one is the sinusoidal wave. This was a new one. This was a challenging one from last year. Sinusoidal wave. The parent equation is just y equals sine x. The equation we have over here has all the parameters in it. This is a k value, that too. This is a d, this is a c. It doesn't have an a. An invisible a value of 1 would be there. So this would have all kinds of other stuff going on, but we only have to graph the parent here. So remember, the parent function has a period of 360 degrees. There's 180. And it has a maximum of 1 and a minimum of -1. So when I graph this one, I know that the sine wave on the y-axis starts at the origin. That's really important to remember. It starts at the origin, which means one cycle later it's back there again because it repeats after 360 degrees. So 360 degrees, I'm going to put a dot here because it's going to be back there again. So sine wave at 180, halfway through, is back there. It's going to change direction. So the sine wave comes up, goes down, and back again. So there's the sine wave. And because this is one, of course, that we did last year, yes, it is a function. It's called the sinusoidal function. You had a whole unit on that last year, so definitely a function. It passes a vertical line test. The next one is a line. The parent equation for a line is y equals x. That's the parent graph for a line, so x and y-axis here. There's x, there's y. My equation of the parent graph has coordinates 1, 1, 2, 2, 3, 3, 4, 4, and so on. It's this, imagine this is straight and going through the origin, it's this line right here, y equals x. That's the line y equals x. And is it a function? Yes, it's the first function that you learned. It was a linear function. Okay, let's look at the horizontal line. Horizontal line. Here's an example of a horizontal line, y equals 6. So we don't really have a parent equation for the horizontal line. I guess you could say y equals 1 would be the parent equation, but a horizontal line, so x-axis, y-axis, Horizontal line means I'm just going to draw a horizontal line on here somewhere. I'll do the one that is actually given in the question, which is a 6. Y equals 6, so let's say 6 is here. There's y equals 6. That should be perfectly horizontal. I should be using a ruler. That's y equals 6. So there's a horizontal line. Is a horizontal line a function? Yes, it is. Passes a vertical line test, so it's a function. What about a vertical line? Vertical line. So vertical line, x-axis, y-axis. Let's draw this one here. X equals 3. So I'm going to go along the x-axis to 3. 1, 2, 3. There's 3. And then my pen. Okay. Right, I could keep going, make lots of spots. I only need 3. So x equals 3 means it's crossing the x-axis at 3, and it's a vertical line like this. So there's your vertical line. Is that a function? If I drew a vertical line, to use the vertical line test, right up here in the instructions, remember the vertical line test is a good way to test the vertical line test. Is it a function? No, it's not. Because if I drew a vertical line through this line, if I drew a vertical line through that line, it's going to cross everywhere. So it's not a function. Let's go to the next slide. We've got the radical or the square root function. So the parent equation here is y equals root x. That's the parent equation. That's no transformations. Oops, that's not very good. Let's try to straighten that out. I'm going to just draw mainly the first quadrant because that's where the parent function is. So parent function of the square root function, you learned this one last year. It's got coordinates 0, 0, 1, 1, 4, 2. So what you're doing is to come up with an equation or a coordinate, you sub a value in. So let's sub in a value like 4. We sub in a 4, we get a 2. That means we have the coordinate for 2. So you can do a few like that. Just sub in ones that work, like 9 and 0 and 1, 16, and you will have one sideways flipped over kind of leg of a parabola is what that is. It's turned over the wrong way because it's actually the inverse. So there's the parent graph. Is it a function? Yes or no? Yes, it is. It's one from grade 11. That's a function. Next one is reciprocal. The equation I gave you here is quite challenging. We will do ones like this later in the year, but right now the reciprocal parent equation we have is y equals 1 over x. And we already did this in an earlier example, so we'll do this one a little more quickly. We've got our y-axis. Here's our x-axis. Now the reciprocal function has asymptotes. So right here down the y-axis, I have an asymptote, and that is x equals 0. That's that asymptote. I have another asymptote right here. It's a horizontal one, so it's y equals 0. And then my graph itself goes in the two diagonally opposite quadrants. So that is y equals 1 over x. Is that a function? Yes or no? Yes, it is. So even though it has an asymptote, it doesn't mean it's not a function because it has an asymptote. The asymptote actually forces it to be a function by not allowing those two branches to cross over each other and get in each other's way. So it's still a function. Exponential. Exponential. Okay, the parent graph for exponential is y equals 2 to the power of x. Now, when we did word problems, we had y equals a times b to the power of x. Remember that? But we're just going to stick with the basic one here. Sorry, I forgot it was square root function. Just to mention back up at square root function, we always do the positive square root function. We don't Otherwise, it's not a function. If I did plus or minus here, then it would not be a function. But like the question I gave you here, if there's no symbol in front, then it's a positive. If you see a plus or a minus, then it's not going to be a function. Back down to exponential. So let's draw a x and y axis. So this one we haven't talked about yet today. Let's see what we remember from grade 11. Subbing in, you can always sub in. If you can't figure out a value, you can always sub in. So let's sub in an x value of 1. If I sub in an x value of 1, y is going to equal to 2 to the power of 1. That's 2. So I'm going to have the coordinate 1, 2. So there's a coordinate there. If I sub in a 0, I'm going to get 2 to the power of 0, which is 1. So 0, 1. And then if we sub in a negative 1, 2 to the power of negative 1, hopefully you remember what that is. That is 1/2. So that's down here. So our exponential graph is, oh, I lost my pen, there it is. My exponential graph is like this. It also has an asymptote. It has an asymptote right along the x-axis. It will never, the parent graph will never have negative y values. It's always going to stay up there. The asymptote is a part of the graph, just like it was for the reciprocal above it. If you are asked to draw one of those graphs and you do not put in the asymptotes, you will lose marks. They have to be there with a dotted line drawn with a ruler. They're an important part. So those coordinates that I put on here are from the exponential graph. Is it a function? Yep, it's a function. We'll pass a vertical line test. Last one is the absolute value function. Absolute value, we haven't talked about that yet today either, so let's start off with x and y. The parent equation is y equals the absolute value of x. So this one has an a value, that's hard to see, and a c value. We don't have any parameters in the parent function. So let's just put a few quick marks on here and just sub in some values to remind you of it. Hopefully you remember it and you could just graph it, but if you didn't remember it, what the absolute value function does is, let's say we sub in a x value of -2. The absolute value, those straight brackets, what they do is they take anything inside that's negative and they make it positive. So if I sub in a -2, for my input, my output will be a +2. So I've got -2, +2. If I sub in a -1, I get a +1. If I sub in a 0, I get a 0. If I sub in a +1, I still get a +1. It doesn't change positives to negatives, it only changes negatives to positive. Everything has to be positive. So these dots can be connected with a straight line. They are two straight linear pieces that are connected in a V shape. So they're perfectly straight here, these pieces. So that's y equals the absolute value of x. And it is a function. Okay, so that's your chart, and hopefully you pressed pause as you needed to, because I might have gone too quickly and you weren't copying it down, but if you haven't, then just press pause now and back it up and go over it again, because that's your review of the main functions we have done in grade 11. So you definitely need a good refresher of that piece there, and you might need to watch this a few times to just remind you of those parent functions. Remember, when in doubt, sub in. If you can't remember how to graph a function, then, and I did that here a few times, right? I just subbed in points. So if I couldn't remember how to graph the exponential, well, I subbed in a few points to get them. So you can always sub in. It can be time consuming if you don't remember how to draw the parent ones quickly, but it does work. I did here too. Sometimes you just need to remember a few of them. Oh yeah, I sub in a 482, I remember now. And you can graph it quickly. If you can remember kind of the shape of it, you might just need one or two coordinates to get you started. So your homework is the handout, and I suggest you do all questions for review A and B. You don't have to, but pick what you need if you don't have a lot of time tonight, and we've got to keep moving forward. But reviewing your grade 11 material is important, and maybe you have a journal or you have some review sheets from last year or even some tests that you can look over to help you remember, because you learned a lot last year. These functions are a lot of functions. We did a lot of transformations with them. So if you want to go over some of that material to help you review, that would be very beneficial. There you go. There's your first review section from grade 11.